Okay, let us start our lecture. I remind you that on the previous lecture we considered the retarded potentials, and these potentials were introduced for the construction of the general solution of the wave of the Cauchy problem for the wave equation. And we considered in particular the cases of such retarded potentials for 3 and 2 dimensions of space. And now we continue with the case n is equal to 1. So we consider the case of one-dimensional space, that is the solutions of the retarded potentials for the wave equation in one-dimensional space, and of course one-dimensional time. And in this case, the fundamental solution takes the form principal fundamental solution of the wave equation takes the following form, and so the retarded potential, which is a convolution of this fundamental solution with the generalized function f, is written as follows. Where I remind you that the function f is in fact a distribution, and it is assumed that it is equal to 0 for negative t prime. And so, bearing this condition in mind, we have t prime must be larger than 0 and t prime must be lesser than t due to this theta function. As for this theta function, it results in the following condition. Which can be written the form. Or another way. So we can write this expression eventually as such. This is the final answer for the retarded potential in the case of one-dimensional space. Notice in conclusion that if the distribution f in all these formulas, that is for the case n is equal to 3, 2 and 1, and in fact for any n, is a regular distribution, a regular generalized function, that is, it is specified by some locally absolute integrable function, then V is a classical solution of inhomogeneous wave equation. the next paragraph. It's called the retarded potential, the retarded surface potentials. Definition of retarded. Definition. The distributions which are defined by the following formulas: V0 and V1. Where E is a principal fundamental solution of the wave operator are called the retarded potentials of simple and double layers with the densities U1 and U0 respectively. The densities U1 and U0 respectively. It is clear that it is clear from the theorems that were proved in the previous semester and that were used already on the previous lecture. It is clear that these distributions are solutions of the unhomogeneous wave equations from the following form. And so our task is to find the explicit expressions for these retarded surface potentials, and we start with the case. We begin with considering the potential V0, and namely with the case n is equal to 3. Let U0 be locally absolutely integrable function, and we consider n is equal to 3. In this case, we just substitute the explicit expression for the principal fundamental solution into this into this formula, and we have to evaluate the integrals, corresponding integrals. Okay, in this case, by definition, the convolution of distributions, we write the following formula. Here, the delta function removes integration over tau, and we arrive at the following expression. We have used explicit expression for this principal fundamental solution, and so we have the following formula. But we can simplify this formula a little bit, taking into account that t is larger than 0, and using the delta function to remove one of the integration. Then we have excuse me, there's a sprint, and the recurrent potential can be written in such a form where we introduce the notation as denotes a sphere of the radius AT with a center at the point X. Then, as for the case n is equal to 3, final answer. Then we will obtain similar formulas for the cases n is equal to 2 and to 1. Case n is equal to 2, substitute the expression for principal fundamental solution that was found in the previous lecture. Delta function removes integration over tau. We arrive at integral And eventually, bear in mind that t is greater than 0, we come to such a formula. Where O is a disk that centers the point X and with a radius AT. And this for the case n is equal to 1, we have and simplifying this formula. And write the following expression. Using the fact, using the fact that t is greater than 0 and simplifying this integral, taking into account the fact that this theta function is different from 0 only in the case when its argument is greater than 0. And we can rewrite this expression in the form. Okay. As for the retarded potential with 0, that's it. And we now turn to the potentials, to the retarded potentials V1. Let us consider the general expression for this retarded potential as follows from its definition. Written in the following form. We can further simplify this expression by using the property which is in fact the definition of the derivative of generalized function. In our case, this distribution is the delta function. Then we can rewrite this expression in such a form. And so we see that this expression, which is differentiated over with respect to t, is just the expression for the retarded potential V0, but with this substitution where we have to replace U1 by U0. And then we can write this expression in the former form. And, okay, but as for the retarded potentials V0, we have already found the explicit expressions, and so we have the explicit expressions for the potentials V1. For example, for the case n is equal to 1, we can write derivative can be easily evaluated, and it results in the following expression. Thus, we have found the explicit expression for all the retarded potentials, V0 and V1. Okay, the next section is called the solution of the Cauchy problem for the wave equation. I remind you that the Cauchy problem for the wave equation looks as follows. We are considering the inhomogeneous wave equation and dimensional space. The time t is assumed to be greater than 0. And at the initial instant of time, we specify the initial generalized coordinate and generalized velocity. Where we suppose that U1 the function f are continuous, and U0 is continuous with all its first derivatives. Now we assume that the solution of this problem does exist, and construct explicitly this solution in the form of certain integrals. And this construction we will prove the existence of the solution of this Cauchy problem. As for its uniqueness, we will take it example. So, suppose that U is locally integrable. Solution of, let me try to use notation. Yes. 20.1, 20.2. Solution of the Cauchy problem. And U of x and t is continuous up to its second derivatives for when t is greater than 0, and it is continuous with its first derivative for when t is equal to 0. Then we will show that if U of xt is a solution of the Cauchy problem, then the following generalized function, which we denote as tilde u, and which is by definition is given by the following expression. Is a solution of the following inhomogeneous wave equation. Let me note that the right-hand side of this equation contains a generalized function and distribution, and so this equation and its solution should be regarded in the sense of distributions. And so in order to show that this statement is true, we need to prove that the following equality holds. That is the action of distributions standing on the left-hand side and the right-hand side of this equation are the same when they act on the same test function phi. I remind you that the function phi is an infinitely differentiable function with a complex pole. It will be relevant for our consideration. And so we will consider the left-hand side of this expression, and we will show that the left-hand side of this expression can be reduced to the right-hand side. And this will prove that this equality is valid, and so the above statement is true. Okay. Let's consider the left-hand side of this expression. Then, by definition of a derivative of the generalized function, we can write the following expression. Namely, we have used here the definition of a derivative twice, and that is why there is no sign here, or the sign is plus. And then, due to the fact that tilde u is a regular generalized function, it follows from this expression that it is this generalized function is specified by locally absolutely locally integrable function. We can rewrite this action of the distribution on the test function box phi in terms of the integral. Then the main idea, or the main trick that will allow us to prove this equality is an integration by parts. Namely, we integrate by parts this expression. Then there will appear several terms. One term will be when this box operator will act on the function u, and then we replace this action by the function f, due to the fact that u is a solution of a homogeneous wave equation. And there will also appear the out of the integral terms, and we will show that these terms can be cast in the form of the action of this generalized function on the test function. Okay, let us embody this problem. And so we will use modes. Let's adjust the formulas for integration by parts. Star. And as for the special variables, integration by parts with respect to special variables, we will use the second Green's formula. Formula, which is in our notation 6.2. where we take V is equal to phi, and D is taken to be a ball such that phi is equal to 0 out of this ball and on the boundary of this ball. It is clear that such a ball always exists due to the fact that phi is a function with a compass support. Then, as follows from the formula 6.2, we can rewrite this integral as integral of the boundary of D. And this integral is equal to 0 due to the choice of the ball D, namely due to the fact that in D and on its boundary phi and its derivative, and the derivative of phi are equal to 0. So, taking into account that phi possesses a compact support with respect to the variable t as well, all the out of the integral terms which appear as this formula at the upper limit is that when t is put to infinity are equal to 0. So we obtain integral terms. So we come to the following expression. Let's first rewrite the above integral as such type of limit. It will become given for us. Of course, it is an identical transformation. And then we integrate by parts. We have the following contributions. These are the out of the integral terms stemming from integration by parts with respect to the variable t. And here is the contribution, which is equal to f, due to the fact that this expression of this bracket is equal to f, and due to the fact that U satisfy the inhomogeneous wave equation. So then we can rewrite it in the formal form. This is U1 by definition. This is U0. And then such an expression. Which can be written as the action of distribution of the test function phi is the following. Here is integration over t is infinite limits due to the fact that we have introduced the function tilde f, which is 0 when t is less than 0. And so we can rewrite it in such a form. And this proves the fact that the initial quality is valid. Okay, thus we have obtained following remarkable result that the setting of the initial data for the solutions of the inhomogeneous wave equation is equivalent to introduction of the source on the right hand side of the wave equation, which has a special form and acts at the instant of time t is equal to 0 and only at this instant of time. Okay, let me write it. To the initial data. Is equivalent the action of instantaneous action of the source and it must be supposed that u is equal to 0 when t is less than 0. Then, as follows from the above considerations, we will obtain the solution of the Cauchy problem. And because of the fact that all the calculations that we performed above can be carried out in the reverse order. The reverse statement is also true, and this is indeed the equivalence, namely that this statement holds in both directions. And thus, we have obtained the classical solution of the problem. As a solution of the equation for generalized function. This equation was 20.4. In fact, this was equation of such a form. Where, by definition of the function tilde u, is this function tilde u is equal to 0 negative t. But as for the solution of this inhomogeneous equation, we have already found the solution to this equation in the previous sections, namely they are the retarded potentials, and in section in the above sections the previous sections we have found the solutions to equation 20.4 for the cases f is equal to f is not equal to 0 and u0 and u1 vanish. And this is the retarded potential V0. And, excuse me, this is the retarded potential, simply. And as for the case when f is equal to 0 and u0 and u1 are not zeros, then these are the surface retarded potentials. And we have found the explicit expression of these potentials. So in order to obtain the solution of the Cauchy problem, the general solution of the Cauchy problem, we just have to add the respective expressions for these retarded potentials. And the result of this summation is the following theorem. That the function f is continuous with its second derivatives. This belongs to the class C2. u0 of x is continuous with its third derivatives. u1 of x belongs to the class C2. This is for the keys when n is equal to 2 or 3. As for the keys n is equal to 1, we suppose that belongs to the class C1, U0 is from the class C2, U1 is from C1. Then the classical solution of the Cauchy problem is this. Is unique and is given by the following formulas. These formulas have names, and these names are different for different dimensions of space. We start with the case n is equal to 3, and then will be the case n is equal to 2, and so on. Kirchhoff formula. In fact, we already obtained all these expressions when we considered the retarded potentials. And all the notations are taken from those formulas. For example, this is the retarded potential V, this is the retarded potential V0, and this is the retarded potential V1. Okay, the next formula, when n is equal to 2, this formula is called the Poisson formula. It has the same structure as the formula above. again, this is the retarded potential V, V0, and V1. And as for the case, the rest case, n is equal to 1. Then down the forward. Is written in a rather simple form. Okay, that's it. And so these formulas provide a general solution for the Cauchy problem for the wave equation in terms of the integrals. In some cases, when the functions f, u0 and u1 are simple enough, then one can evaluate these integrals in a closed form. But in general, of course, one have to evaluate these integrals numerically. What is a rather simple task and can be realized on computer. Okay, and some simple examples. Yeah, this was a remark which was already mentioned. These solutions were found by us explicitly. But as for the uniqueness, it was not proved, and we will take the uniqueness of this, the solutions of the Cauchy problem without. Okay, consider a particular case. When n is equal to 1, f is equal to 0, and u1 also vanishes. The number for is reduced to the following form. Let me continue our lecture. So we consider the particular case of the above formulas when n is equal to 1 and f and u1 vanish. And in this case, the solution of the Cauchy problem for the one-dimensional wave equation is written in the following form. And we see that the function that defines this, specifies this general solution depends on a certain combination of x and t, and so the definition. The lines which are defined by these two equations are called the characteristics. wave equation for n is equal to 1. Another definition. The function u0 of x minus 80 is called the forward wave. Whereas the function 0 depending on x plus 80 is called the backward wave. The backward wave propagates with the same velocity as the forward one, but in the opposite direction. Namely, the forward wave is constant on the characteristics x minus 80 is equal to constant and moves to the right with the velocity a. And as for the backward wave, it is a constant on the characteristic x plus 80 is equal to constant, and it moves to the left with velocity a. And thus, in such a way, we have obtained the interpretation of the constant A. As I said in the previous lecture, when the wave equation was introduced, the constant A, positive constant A, characterize the velocity of propagation of perturbations described by the wave equation. And now we show this explicitly from this formula, for example. And let me consider another example. The graphical solution of the wave equation when n is equal to 1. We consider the following problem. Consider a homogeneous wave equation, and with the following initial conditions. We assume that the initial instant of time, the function u is equal to some given function g of x, and as for the generalized velocity, suppose that it is equal to 0. In this case, one can solve the Cauchy problem in a graphical way. Namely, let me draw a picture. There is x, and we know the analytical solution for this problem. It is given by the formula. I remind you here. So at some initial instant of time, we have, for example, such a profile. It is a function g of x. Then, in order to find graphically the solution u depending on x and t, we have to divide the heights at every point of this plot. For example, take point here, find its height, and divide it by 2. And so at every point, we obtain such a curve. And in fact, as follows from this formula, this curve this curve defines the profile of the function u0 of x. And then this profile moves to the right and to the left in accordance with this formula. And as for the wave that moves to the right, it is a forward wave, and as for the wave that moves to the left, it is a backward wave. That is when t is greater than 0, we can draw a following picture. Greater than 0. For example, such a form. I'm considering here the case when these two waves are in such a particular position. Then, in order to find the function u, one have to add these two plots graphically, and in this case, oh, this is some degenerate case. It's not so interesting. Let me consider such another representation of such a form. And where we add them graphically, we obtain such a profile. Here is a forward wave. Backward wave. And here is the result of the addition. Okay, and so now we consider another particular case of the bound general formulas. Namely, we consider the so-called spherical waves. And the next section is called spherical waves. Spherical waves. Let us consider the solutions of homogeneous wave equation, and we will consider only the case n is equal to 3, and I will comment on the cases when n is equal to 2 or 1 further. And let us seek the solution in the form when u depends on x only in the form where r is a modulus of x. Here is definition. The solutions of such a form of this equation are called the spherical waves. It is clear that the constant of the surface of a constant phase for these solutions is a sphere, and this is the reason why they are called spherical waves. These solutions represent an important class of solutions of wave equations, important from physical point of view, due to the fact that sufficient distance from the source of waves, for example, from the antenna, or from some other source of electromagnetic waves or sound waves, all the waves turns into spherical waves with when r tends to infinity, when the distance from the source tends to infinity. And so we will consider these solutions in more detail, and let us find the general form of these spherical waves. To this end, we consider wave equation and let us change a system of coordinates and write this equation in the spherical system of coordinates. Now we consider only the case when u depends on r and it doesn't depend on the angular variables. Then this term vanishes and we are left with such a combination. Which can be written in the following form. The result, this equation for spherical waves takes the form or it can be written and multiplied by r as follows. Then if you introduce a new function, v, which is by definition r times u, this equation is reduced to one-dimensional wave equation. Thus, we see that the spherical waves in 3 dimensions are described by one-dimensional wave equation. After a suitable change of after introduction of suitable notation, we introduce v, which is r times u. Then now we will find the general solution of this equation. To the same, we change the variables here, and in fact we reduce this. We will reduce this equation to a second canonical form. This is a wave equation, hyperbolic type equation in its canonical form, but we know that there are 2 canonical forms of this equation, and the second form is obtained by the form change of variables. These variables are called the light cone variables. Psi and eta are given by the following expressions, and the reverse, the inverse, change of variables looks as follows. Then the derivatives are transformed in accordance with the following formulas. It is just a chain rule for differentiation of functions, and then we have just take a square of these 2 derivatives because they commute, and we obtain as for derivative with respect to r, the following formulas. Then, substituting this and that into the wave equation in this form, and equation we obtain. This equation is equivalent to equation of such a form. Of course, it can be written, for example, in such a form. Then it follows from the such notation that the derivative of the function v with respect to eta is some function depending on eta, this equation means that V eta doesn't depend on psi. That is, it is some function of eta, the second variable. Then we integrate this expression with respect to eta and obtain that this integral can be represented in the form. In fact, this is the integral of c of eta, but due to the fact that we integrate with respect to eta, we can add an arbitrary function. Oh, this is the definite integral with respect to eta. But due to the fact that we integrate with respect to eta, we can add to v an arbitrary function dependent on psi. And one can check that this is indeed the solution of this equation by differentiating with respect to eta. So the general solution of the one-dimensional wave equation looks as follows. It consists of two functions, and in fact they are just the forward. Let me write such a form. When we restore the initial variables, we have the initial function u. Thus we see that the general solution of the one-dimensional wave equation is a sum of forward and backward waves, as was defined, in the previous section. And as for the function u, initial function, it describes a spherical wave, is written in the form in fact, it is a general form of a spherical wave. We see that the parameter A can be interpreted that it is in fact A is the velocity of propagation of perturbation of a spherical wave. Okay, and this general form is valid only in the case when the problem is solved in the region which doesn't include the origin. This is when the point r is equal to 0 is excluded. But in the case when this point is when we solve the problem in the domain which includes this point, then we see that in general position this function tends to infinity when r is equal to 0, because this combination is not in general 0, whereas here we have division by 0. So then y is equal to 0 belongs domain D where the wave equation is solved. We must impose a certain restriction on the form of the function f1 and f2 due to the fact that the function u is assumed to be a regular function. Let us find this restriction. For example, excuse me, let me comment on the fact when R doesn't belong to the domain D. This is the case, for example, for the problem, for the outer problem, when one solves the wave equation out of some region D, which includes the origin. And in this case, the function f1 and f2 are arbitrary, because the point I is equal to 0 is in fact excluded. But when it is in the domain D, then we must impose these restrictions. Okay, and let us represent the function f1 and f2 near the origin of the system of coordinates in the form of Taylor series. We have the following expansions, and then we substitute these expansions into this expression, and we have near the origin thus it is clear that in order to provide regularity to the function u at the origin, one must require that f1 is equal to minus f2. Yeah. Let me finish at this point. And this was the last lecture in English, and the following lecture will be in Russian. Okay.